Today we're going to be talking about connections, structural steel connections, and it's the design to NZS 3404. We'll be looking at the Redco spreadsheet, the SCNZ handbook and the online tool, and Bentley RAM Connection software, as well as looking at some Mathcad files. So let's begin with the Excel spreadsheet, and there it is. It's blank. There is no Redco Excel spreadsheet for connection design. You have to make it yourself. Well, I suggest you don't do that. Your first port of call when you're dealing with connections is this. This is the SCNZ handbook and online tool. So this was developed following their publication of their connections design handbook, and it contains most of the information, or the results of most of the information that's in the handbook. You'll need a login, and once you've logged in, you can go to the site and pick out from a pull-down list. So here is your selection list. Pick a category. Let's start with universal beams. What sort of size do we want? Let's have a 360 universal beam. Pick out the mass, and then pick out the connection. So these codes are a little bit cryptic, so I'll explain those a little later. So let's say we want an AC 1-250 SWC. What on earth does that mean? But we'll select it anyway. And the website tells me it's got a shear capacity of 283 kilonewtons. Well, that's good if that's what you want. So that's a nice little summary of that. So what does it look like? Well, you can review the report. Click on the View Report button, and it spits out a report that looks like that. It gives you a generic diagram or generic drawing of the connection. So in this case, all that cryptic meant was angle cleat connection. So AC means angle cleat. And the 50% was the 50% capacity. So on the left-hand side, you have a summary of the input information. So the size of the member and the size of the angle cleat. By default, it picks grade 250 for your angle cleats. And by default, it picks grade 300 for your member sizes, and so on. And by default, it picks grade 8.8 20mm diameter bolts. So this is basically from a library of ready-made connections. So on the right-hand side, you have the connection and capacity, in this case 283. Well, that's all good. There's also a drawing. So if you click on the View Detailed Drawings, it pops out what looks like a detailed drawing of that particular connection, except it's not that particular connection, it's a generic, and that will explain some of the dimensions, but it's good enough to post in your calculations. Coming back to the home page. Now, not all of the sections have got all of the calculations. So, for example, if I pick my square hollow sections, pick a section size and a mass, what kind of connections have I got? Well, I've basically got a choice of base plates, a BPP base plate or pinned base plate, and that pops out and says I have a connection axial capacity of 420 and a shear capacity of 57. If we look at the drawing, it gives you generic drawings for a generic base plate. So we've actually got a square hollow section, so it's probably one of these things. On the left, you have the same sort of detail for an I section, or on the right, a tube. Coming back to our plate, we can also view the report. And again, we have information about the connection design and the connection capacity. Okay, we can come back. We can view that report, and we can view the detailed drawings. Now, if we select another type, say the BS4 universal beams, and it has the section sizes in there, but it won't allow me to design it. So it's designing connections which are basically standardized and standardized from a template. And what sits behind all this is the information that's contained in their online handbook. Now, some of these cryptic clues for the connections you might work out from this button here, the detailing constants. And for example, your SCNZ, so angle cleat with no cope, and that gives you some detailing constraints in there. Okay. Back to the show. So that was the SCNZ handbook and online tool. So that's your basic starting point if you're designing connections in steel design in New Zealand. And it's a very quick and easy tool for designing and checking the basic connections you will have in many building frames. Connection types, as a reminder, this isn't really posted on their website, but it's buried in the handbook somewhere. So the WP, it means web side plates, and the FE means flexible end plates, the AC means angle cleats. So it might be worth taking a screen grab of this right now. And then we have MEP for moment end plate, MEPS for moment end plate splice, and so on. And we go on, BWBS for bolted welded beam splice, and so on through to our BPP, which we've seen as our base plate, which is pinned. Okay, that was the online tool. Now for something slightly more sophisticated, the Bentley RAM Connection software. So let's switch over to that. And as I said, going through it, I could probably spend an hour on various tutorials on this. And so keep an eye on the YouTube channel because I probably will be posting a few more as we go. So when you fire it up, this is a RAM standalone version of the RAM connection, and you need to be signed into your RAM Bentley login, and you're presented with an interface like so. Most of the buttons you probably won't deal with most of the time. So we start with the connections template. So if we click on the connections template, it shows what templates are going. And that's a clue to how this software works. It works by picking out a ready-made template, a template of connections that they know have worked before. And then you compare it with the loads that you've put in. Similarly, sections. Here is my library of sections. Well, I don't want the US. I want Australian connections because that's what we're going to be using. Materials. We've got Australian materials in there, so they're likely to be the typical range of material types we use in New Zealand. And similarly, the connection types are the templates that we'll be using to define our connections. And similarly with bolts, we want the Australian code for bolts. Let's go to Australian sizes and so on. So similarly with welds and anchors. So for this part, you'll probably never use it again once you've set it up. And hopefully your administrator of your IT will have already set this up properly. So we have a blank screen at the moment, and it has multiple ways of doing the same thing. So if you want a new connection, we click on the button marked New. And up pops a selection of different types of connections that you can design with this software. The software is limited. It doesn't do every connection and every possible permutation, but it does a number of standard, typical connections that you'll find in steel construction. So top of the list is the beam to support, and you've got various ways of connecting a beam to a column, or beam to a beam to a girder, and so on. You've also got splices and column tops and bottoms, as it were, the column cap and the column base plate, as well as vertical bracing or horizontal bracing, and then truss components. So this is quite useful for tubular trusses. Let's start with something simple. Here is a beam to support, and we'll go for the most basic one, a beam to a column flange. So let's select that. Now, if you punch in the data, click on OK or click on the next arrow, we find it's picked out your beam size, and it's picked out a 310 UB32 size, simply by default. You can change that from the pull-down menu, make it either bigger or smaller. Let's make it a little bit smaller, click OK. And by default, it's picked out the 350 material. Well, you can change that to 300 if you so choose. Similarly with the column, you have a prismatic member. It's picked out a UC 200 UC 52.2, and again you can change that by the pull down menu, and you can change the grade in pretty much the same sort of fashion as done before. So there's your beam and there's your column. Now you would be tempted to go on to the next part, which is loads, and that would seem the obvious thing to do. Click on loads and you're presented with a sheet for putting in your loads. Now, you can only use one load combination, the load combination that you've defined for this set. And at the moment, you haven't defined any load cases. But if you've designed your connection or you designed your frame in another package, that will spit out the loads that you can use in terms of a loading envelope. So you might be okay with just one load case in there. So handily, they have help files, and the help files are context dependent. So a little bit of help will pop up whenever you put information in to Bentley RAM Connect. There isn't a generic file called help for the whole system, so you have to do it bit by bit. But now we've got V2 and we can look on the diagram. Oh, look, the beam has a V2. Let's give it a value of 35 kilonewtons. We'll give it a nominal axial load, as we can tell from the diagram. We've got 0 moment because it's a pinned connection. Look at the column. Well, we'll probably have a nominal 21 kilonewtons of shear, and the axial load we'll put is 67. Quite randomly, and again a 0 moment. So if I click OK to that, it presents me with this image, and that shows me I've got a column and I've got a beam, and that's about all it says about it. It knows it's going to be a beam to column flange, but it doesn't tell me how I'm going to design it or check it or what the value is. So again, we've got the templates on the right hand side. Well, we can ignore those if we wish by clicking the template button off. On the left hand side, we have our a picture of the connection we're going to design, and it tells me it's not designed. So we can go straight to the design, or we can add some more loading. Now, if I click on the add/edit button, it tells me I can add load conditions, and by default I've got 1. So what you can do is add load cases, and these tiny buttons down here allow you to apply a number of different load cases. So by default it gives you dead load, but you can add live, snow, wind, and so on. So if I click add into there, similarly with load case combinations, I can either delete them or I can add them. And give it a dead load of 1.2 and a live load of 1.5 factored in there. So it's already given me one combined load case at the ultimate limit state. There is an auto-generate feature on here, but it doesn't work for the New Zealand code. It's aimed at the American code. Okay, so I've got my load case combinations in. I haven't actually put any loads on that. So the generate load case combinations doesn't actually work for New Zealand codes. Okay, so now what do I do? Well, I want to apply something to it, some bolts, some cleats, and so on. So I might want to click on the Design tab. It's not fairly obvious that. So thankfully, we've already got it defaulted to NZ3404, and we assign by clicking on the assign button. Now there's a number of different ways of doing it, and again you're pulling from libraries. You've got the basic connections, the smart connections, and the user connections. Well, surprise, surprise, there are no user connections. After a while you may be able to build up some user connections. What's the difference between the smart and the basics? Well, it's a bit like the difference between manual transmission and automatic transmission. There are a number of the standard libraries which you can optimize, and if you pick a smart connection, you will also get a button marked optimize in there. So if I go stick with my basic connections to give me a bit more control, the first out of the box is an angle cleat. So if I click assign to that, and that assigns the angle cleat to the column. Okay, now by default it's showing me down in tiny letters on the left hand side 0.4 of my user case. Okay, so how do we know what's going on? Well, there are two routes to get to the details of this. One is you can click the edit button and open the edit function, or you can double click and that reveals a new window which gives you access to a 3D view of your connection. So you can pull it around by twisting on the axes, or if you click on the big cube, you can take some standard views. So there we have our standard views, and you can scroll in and scroll out. Across the top we have some basic information such as save, print a file, and so on. The interesting ones are the results tab and the data tab as well. You can change the view that you're looking at depending on which button you're pressing here. I prefer the solid view. More importantly, on the right hand side you have a number, a 0.4. The 0.4 is the utilization factor of this connection. So it's less than 1, so therefore it might indicate that the connection works. However, it's not green, it's kind of orange. So it's giving you a warning. On the left-hand side, we have all the information about the connection. So we start with the members, which tells me about the beam that we've selected. Have we coped it? In this case, there's no copes on there. Also tells me about the angles. The angle is picked from the library as 100 by 100 by 8 equal angle. Okay, by default it's picked out an M20 grade 8.8 bolt. So it seems okay so far. So what's wrong? Well, let's click on the results button. Now pops a report. So this is your RAM connection report about this particular connection. It tells you what the input was. I only put in the dead load, which has just been factored. And I've got lots of green ticks, but a couple of red crosses. So it's checked the support flange end distance and the angle thickness it doesn't like. So it would appear that my connection is strong enough, but it doesn't actually fit and it doesn't comply with the detailing. So let me close that and go back to the potential design. Now you could play around with the size of the cleats, or you could do something else. You could change the type of connection you've got. So let's come out of that by clicking the cross, and I want to assign the connection to a different thing. So let's go for a flexible end plate instead. So that's now been assigned. Double click to open it out. Let's have the 3D view of that connection. And now you can see I've got a 0.29 capacity, utilization of the capacity. So if you look at the results, I've got the same sort of information now, but with lots of green ticks. In fact, the utilizations are also quite low. But if you're happy with that, just go ahead, print that out and save it. So you can save it as text or put it into Microsoft Word or Excel, or you can just print it to PDF or to your printer. Fair enough. Or you might want to change it because that's not very efficient. So your end plate, scroll down here on your left, you've got an end plate thickness of 8mm, and you've got M20 grade 8.8 bolts. Well, let's see how low we can go with that. So let's go to the other extreme. Let's try M12 grade 4.6 bolts. Now, it's still telling me it's working. So I've got a 0.69, so it's working a bit harder now in there. And as you go, the help file will pop up and it reveals itself down below. And it's also context sensitive. So when you're looking at bolts, it will show you the picture of the bolts. Hopefully, if you're looking at the plates, it tells you about the plates. If you're looking at the longitudinal spacing, it tells you about the spacing, gives you a picture of each of the bolts. The other button on here is the data. So if you click on that, you get a report for all the input data. So that tells you all about the beam and the end plates you've entered in here. Okay, so that's relatively straightforward. You've designed your connection. If you've made any changes, don't forget to save it. Otherwise, you'll be lost when it comes out. That will be lost. So you've got two views here, and you can have the 3D view that we've got, or you can switch to the DXF view. If I switch off the help, you get a full page. So this will allow you to export this connection to your drawings, your CAD files as well. Close that, we come back to our connection. So that's the basics of RAM connection software. And in common with many Windows software, you have open, file, save, and so on down your left-hand side, and it follows the ribbon method. But it also presents you with some recent models. So here's something I prepared earlier. I won't say the one we had. Here's something I prepared earlier. So I've got a whole range of connections. This was for a real project about a year or 2 years ago. And some of them are relatively straightforward. So here is my BCW, my beam to column web. And it tells me here that I've got a 0.99 utilization factor. Now, that may or may not be true, depending on whether you've got the critical load connection actually set. If you find that the number there is different from the number you work out in your second screen, then you've not probably picked the critical load factor. And you can go on to slightly more complicated connections, such as this bracing connection in here. So I've got tubes connecting to a beam. And if we go into the details of this, you can see things can get quite complicated. But interestingly enough, I've got another button now, and it's called the Optimize button. And if it finds that your utilization factor isn't the factor you want, i.e. you're too large or even too small, you can click on the Optimize button to rationalize it. But it's still telling me, even though I've optimized it, I've still got a warning about edge distances. You might want to do something about that. Unfortunately, because it's a smart connection, you can't. You've got limited editing rights over this one. So we could go on with all sorts of things with this software, but I'll just close that and leave it to you to explore. So before we go into the Mathcad, a little bit more about designing connections. So as if by magic, you can put these steel frame members together. So that's kind of the beauty of steel framing. You have relatively simple connections and relatively simple members that go together with relatively simple joints, in this case, a set of bolts. Now, they don't do it by magic. There is somebody actually fixing that joint. And by way of a side issue, never connect steel members just with one bolt. That's the primary, secondary, and so on, the main members of your beam, because it makes them very difficult to assemble on site. So let's look at the details of the different mechanisms, some of the different mechanisms you'll be looking at. Let's start with bolt shear, one of the simplest. You took two pieces of metal, you put a bolt between them, and you can transfer the load, and the shear is on that plane there. The next we look at the bolt bearing. So the bolt is bearing on the little bit of metal around the bolt, and as you apply the load is increasing to transfer the load from one component to the next. Okay, that's relatively straightforward when you've got uniaxial loading and simply the bolt or bearing. There are other things you've obviously got to consider in terms of web tearing, web buckling, and so on. But let's look at another complicated case, how you distribute loads when you've got eccentric loads within a group of bolts. So it's quite nice and simple when you've got a concentrically applied load, so applied through its centroid, and the load in each bolt is simply the full load divided by the number of bolts. So all bolts are carrying the same load. Now, if you increase the eccentricity, you're inducing a moment, and so therefore the load in the bolts increases as a proportion of the distance from the centroid. We can break that into two components, the concentric load and the eccentric load causing the moment. So let's look first at the concentric load, and as I've mentioned, you just take the full load and divide it by n, the number of bolts, to give you the reaction in the bolt. And so for equilibrium, the sum of the horizontal and vertical forces should balance out. Now look at the moment arising from the eccentric load, and the load in each bolt is proportionate to the distance from the centroid of the bolt group, and the resulting force is the moment applied multiplied by the distance from the centroid divided by the polar moment of inertia of the bolt group. Now the polar moment of inertia of the bolt group is simply the sum of the distances of the bolts squared from the centroid. That can be broken down into an x and y direction, so you can have an Rx and an Ry. We do that so we can combine it with the load we derived in the concentric load. Okay, nice and simple. So you're deriving something simple from something that's quite complicated. But what you normally do is you design for the worst load case. Similarly, weld force distribution. If you've got an eccentric load applied to a weld, you can break that into two. And we start by applying the concentric load, P, and this applied through the centroid. And you just take the applied load and divide it by the total length of the weld to get the force per unit length in the weld due to the concentric load. Now let's look at the eccentric load. So the moment induces a varying reaction around the weld group, and the reaction per unit length is proportional to the distance of that weld from the centroid of the weld group. And again, your reaction in your weld is equal to the moment multiplied by the distance from the centroid divided by the polar moment of inertia of the weld group. And you can split the polar moment of inertia into the x and y components, giving you a resultant force in your weld per unit length that's dependent in an x and y direction. We now come on to the Mathcad, and there are many of these Mathcads I've done. I'm going to limit you to about 3, given the sort of time we've got. So I will open up Mathcad. Start with the fin plate. So here is the Mathcad file for the design of a fin plate connection in accordance with NZS 3404. So we've already got our forces derived from a separate analysis. And we're assuming we're going to be using M16 bolts and a 10mm thick fin plate with 6mm fillet welds all round. So as I say, our applied shear load is 40 kilonewtons. We're using a primary beam as a 310 UC 96. So here are the parameters for that. The secondary beam is a 200 PFC. Here are the dimensions for that PFC. Fin plate, as mentioned, is 10mm thick, and we've got 2 bolts. I'm going to use the same grade of steel for the sections as I am for the plates, so it's going to be a grade 300. Let's go to the bolts. We've got 16mm diameter bolts, and they're going to be grade 4.6, giving us a tensile strength of 400. First, we need to check on the fin plate bolts. That's the bolts in the fin plate. So we're assuming that the bolts are in the threaded portion of the bolt. So the shear plane goes through the threads rather than the shank. So we add up the areas of the threaded portion multiplied by the number of bolts, multiply that by the tensile strength of the bolt, and it has a 0.262 factor to give you the shear strength of that bolt group. Apply a strength reduction factor and we get a design capacity of 62, which is significantly above our applied shear. Now let's look at the weld. We have a 6mm weld, which gives us a throat thickness of 4.2 millimeters. And we know what the nominal capacity of the fillet weld is per unit length, taken from the code, clause 9.7.3.10. And that gives us our 1043 kilonewtons per meter for that weld. So the nominal capacity of the fillet weld and is just the length of the weld and multiplied by the nominal capacity, and because we've got a weld each side, we double it. That gives us a 367 kilonewton capacity of that weld. Let's look at the fillet weld resisting shear, and we have a utilization of 18%. Check on the fin plate resisting the shear. So the shear capacity of the fin plate itself is simply the shear area multiplied by the yield stress multiplied by a 0.6 factor. That gives us a design shear capacity of 347 kilonewtons, so quite large. Need to check the bearing. So you've got bolts bearing on the ply of the fin plate, and so the bearing capacity when given a strength reduction factor is 176. And we've got our bearing capacity simply by the diameter of the bolts with the thickness of the plates multiplied by the tensile capacity of the steel. If you've got a thin plate, it may buckle in shear, so you need to check shear buckling. So clause 5.11.5 gives you a factor for shear buckling. In this case, the factor is well over 1, so shear buckling is not going to be a problem with this particular plate. You take the minimum in any case, and then you have a design shear capacity, which is below your applied. So you can summarize that by saying your design capacity of the connection is 62.3 kilonewtons. Okay, nice and simple. You can go on to the next one. Look at it. Here is the Mathcad for a welded portal knee, and this is common in house frames. So we're doing it again in accordance with our own code NZS 3404. We've taken the values of the forces from a separate analysis. And the design philosophy is that the applied moment is resisted by tension in the butt welds connecting the tension flanges, and the applied shear is resisted by the fillet welds in the connector of the web stiffener. So what do we need to check? Well, tension in the butt welds due to applied bending moment, shear in the fillet welds due to applied shear, and shear yield in the web. So here's our connection geometry. Our beam and our rafter is 200 PFC. Our material properties, as before, we're using grade 300. We have a 6mm fillet weld. So we can derive, as before, the nominal capacity of the fillet weld multiplied by the length of the weld, and gives you a design capacity when you apply the strength reduction factor of 220 kilonewtons. We have a butt weld, which is the same thickness as the plate, and so it's 12 millimeters. We're assuming that the butt weld strength is the same strength as the material you're using for the main sections. So your nominal capacity of your butt weld in the flange is 387, and the design capacity when you apply your strength reduction factor is down to 232. So let's compare it with the loads we've extracted from another piece of analysis software. So we're applying axial load, shear and moment to this connection, but we're also pulling out from previous calcs the nominal bending moment capacity or the buckling moment capacity of that beam. Why do we do that? Because we need to check the minimum connection forces. So for frames not subject to seismic loads, we look at clause 9.1.4. That gives us the minimum connection forces that you need to design your connection for. If it is subject to seismic loads, you need to look at clause 12, and that will give you the minimum connection forces for that. The reason behind this is you have a building frame and you want it to be robust, and so it's about avoiding a disproportionate collapse and progressive collapse. So you want to basically tie your building together, your frame members of your building together with at least the minimum forces. So your applied moment, your applied shear is going to be either the minimum of the applied loads or the minimum loads that you've put in, calculated from clause 9. So we begin with a check on the butt weld resisting bending, and so the tension forces in the flanges are simply the applied moment divided by the lever arm. So this is the depth and the distance between the centroid of the flanges in this case. Look at the fillet weld resisting the shear. So we know what our applied shear load is and our shear capacity of that. Check on the web shear and we compare that to the capacity, and in each case we're below the capacity. Okay, for a final one, this is a splice. So this is a beam splice. So here is the Mathcad for the design of a beam splice in accordance with NZS 3404. And we've already derived the member forces from a separate analysis. The design philosophy that we're using says that the applied moment is resisted by the flange plates, the transverse shear is resisted by the web plates, and the axial force is divided equally between the web by the flange plates. So therefore we need to check the flange plate capacity in both tension and compression, the bolt shear, the bolt bearing, the flange capacity, and the web plate capacity. And as an aside, I didn't make up these design philosophies, by the way. These have come from the NZ Steel Construction Handbook. And so for their example connections, they do set out what the design philosophy is for each of the connections. So we put in our connection geometry, and we're using, again, a 200 PFC, and we're using M16 bolts of grade 8.8. We scroll down, we're using a 70 by 12 mil flange plate, and there are bolts on either side of the connection to make up the splice. The splice also has web plates, and those are going to be 170 by 6 mil thick, and there's two bolts on each side of the connection. So our material properties, again, we're using the same material for the section size as well as the plates, the flange plates and the web plates. If you have different grades, you need to separate these material properties. It just makes your calculation simpler if you use the same grade. So our applied loads from the analysis, once again, we check our minimum loads as taken from the code, clause 9.1.4, or clause 12 is subject to seismic loads. And we design for either the applied loads or the minimum loads. So we begin with a check on the flange plate resisting the bending. And it's the moment applied divided by the lever arm. And we can see that the stress in the plate is below the yield stress. So, okay. Check on the flange plate bolts. So the bolts have a shear capacity that we've seen before. We take the yield or the ultimate tensile strength of the bolt multiplied by the area multiplied by 0.26. There is a factor if you've got lapped connections. That's taken from the code. You've also got a web plate resisting the shear. So check the shear capacity of the web plate. So it's a shear area multiplied by the yield multiplied by 0.6, multiply it by a strength reduction factor, and that gives you 115 shear capacity. Check the ply, the bearing of the ply, and again you're looking at the diameter of the bolt and multiplying by the thickness of the ply, the web plate ply, and by the strength of that web plate. Okay, and we find it's below the applied shear load. Check if we've got a slender web, in which case shear buckling might be a problem. So we calculate our alpha V value from clause 5.11.5. And with that, we find that our design applied shear is lower than the design capacity. Let's check on the web plate bolts themselves. We've got a shear capacity in the bolts as derived similarly to how we derived above. And we have a design shear capacity of the bolt group of 129 kilonewtons. So again, we're okay. Okay. There are more, but I'll spare you that. And some are a lot more complicated, including this one. This is a reproduction of the template from SCNZ, and it goes on and on and on. I'll spare you that one today, and we'll save that for a separate file. So check out the YouTube channel for future updates to that. Okay, coming back to your steel connections guide. So this is the main reference if you're in New Zealand, and you've got part 1 and part 2. So 1 tells you all the theory and explains how you design connections, and then the other book actually gives you the connections themselves. So if you're not a member, they're extortionately priced, but if you are a member, it's reasonably priced books in there. And if you want to become a member, you go to the Steel Construction New Zealand website and click on the Become a Member. Now there's a corporate membership and there's a student membership as well. Unfortunately, I couldn't find out how much the student membership was. But if you're doing steel connections regularly in your practice, it's certainly worth getting membership. And a little bit more background from my old employer. The Steel Construction Institute in the UK produced a number of green books, as they called them. And so we start with P212 and 213 for simple joints in steel constructions to the British Code and then to Eurocode 3. And then you looked at moment resisting joints to Eurocode 3, as well as composite connections. And those are all available from the SCI shop online. So our next seminar is going to be the bronze method of pile design. We'll be looking at freehead timber piles in a cohesive soil subject to lateral loads.